Section 3.7, our last section in Chapter 3, is a topic called related rates. And what related rates are is they talk about how quickly something changes with respect to something else changing. So in every problem that we're doing, we're talking about how fast something's changing. We're talking about a rate. And rates are derivatives. Okay, so this is an application of derivatives. Some guidelines for solving related rates. Just like with optimization, the first thing we should do is to create a sketch, if there is a sketch to create, if it's appropriate. Second thing, much like in the related rate or in the optimization section, we need an equation that relates all of the quantities together. And that's largely dependent upon the kind of sketch you might have created in part 1. The third thing says that we're going to differentiate how? Implicitly. Ooh, yeah, implicit differentiation. The primary reason we did implicit differentiation is to be able to do something with it. And we haven't done anything with it yet. This is actually an application of implicit differentiation. There's something different about it here, though, so be aware. This says we're differentiating implicitly with respect to time. You see, we didn't do that before. We did it with y with respect to x, right? In this case, we're going to do whatever our variables are, we're going to differentiate with respect to time. So it's going to look a little different. The last two steps, kind of in the same thing, are going to be substitute in the values that we know. So we're going to be given information for some of the values in our problem, and in fact all but one of them. And then in the last step, we're going to solve for the remaining value that we need to find, a remaining rate. Okay? So half the battle in working these particular problems is in trying to figure out what we know, what we're looking for, and what we're actually wanting, how we're going to relate the quantities to one another. All right, so here's our first question. We've got a fish, and it's reeled in at a rate of 1 feet per second from a point 10 feet above the water. So just that very first sentence, I'm going to start a picture, all right? So in my picture, I need water. So there's my water. And I know that there is a fishing line that's going out somewhere further out from where I am. So if I'm the one that's fishing, right, the fishing line is somewhere over there by Jamie. Okay, you're the fish, or at least roughly where the fish is, Jamie. All right, so the fishing line is from wherever I am to over there. Okay, so the fishing line is doing something like this. And it tells you that the fishing line, that is the end of the reel where I'm holding it, is 10 feet above the water. So one thing you could imagine is that I'm sort of standing on like a dock or on a boat 10 feet high. That should look perpendicular. It doesn't look very good. Let me try it one more time. That was awful. For some reason my line tool doesn't want to make things perpendicular today. We'll go with that. All right, so this is 10 feet above my water. One thing you have to be aware of when you are doing related rates problems is things that change and things that don't. In this problem, that 10 feet doesn't change. The fishing line is not, I'm not on like a descending dock. The boat is not sinking, however you're sort of describing this. The fishing line is always 10 feet above water in terms of the vertical distance. However, as I'm reeling the fish in, the line, which is my vertical or my diagonal line that's on the screen right here, is changing, right? As I'm sort of reeling the fish in, this line is moving closer and closer and closer to the vertical 10 feet. Can you guys picture that happening as you're sort of pulling in a line of string, or in this case it's a fishing line, that's going to be moving in as you get closer? So this quantity right here does change, so I need to let it represent some variable. We'll call it x for now. Because it is going to change, so it is a variable quantity. I don't need a variable for the 10, because that's not variable. It doesn't change. It is a constant value. The other thing that it talks about in the next part of the sentence is it says, at what rate is the angle of elevation d theta changing? Well, it tells me that angle of elevation is called theta, and that's right there. And that's a trig concept that you should have encountered last semester or before, right? The angle of elevation. That obviously changes too if the fishing line's coming in, right? So it makes sense that we actually give that a variable name, and they're using the variable theta. Okay, so far so good? Okay, there's a little bit more information that we're given in the problem. We're actually told that at some point, so this is the things I'm going to write down that we know. The first piece, I guess, is actually this one. It says the fish is being reeled in at a rate of 1 feet per second. So what they're talking about is that the distance right here is changing by 1 feet per second. Right? It's being reeled in. Like as I'm reeling in the rod, I'm pulling in 1 foot of string for every second that I'm reeling. Does that make sense to everybody? The quantity that is actually then is that's dx dt. That is, it's the rate that the x value is changing with respect to time. And you can kind of think about it in terms of the units that are given too. X is the number of, or is the length of my line, and it's measured in feet, right? And then the t, the time, is being measured in seconds. So we're sort of seeing that ratio written as a quantity that's sort of like the feet per second units. So that's actually a pretty helpful thing. The other thing is that it's actually -1. Why in the world is it -1?
The line's decreasing.
Yeah, the line's decreasing, right? So if the fish were swimming further away, right, that actually could be an increase in quantity. I mean, that would be a possibility if the line were just let loose instead of being reeled in. You could actually have the line increasing in length. We don't on this one. It tells you that it's where I'm pulling the fish in, so this is a negative quantity. That length is decreasing. There's one other thing I know. It actually says there is a point in time where the line is 25 feet long. Now, that's not a fixed quantity, so I'm not going to put the 25 in place of the x right now. But at some point, there is a point when the line is 25 feet out. Of course, at some point, we also hope that there's a point when the line is 0 feet out. So that's just one particular point in time that x is going to equal 25 feet. Those are the quantities I know. What are we asked to find? The rate about theta, and the rate is always in terms of time. You're right. So we're asked to find d theta dt. How the angle theta is changing with respect to time. Does that make sense? Okay. This is a triangle. Agreed? Yes, it is a triangle. In a triangle, there are relationships between these three quantities. What relationship exists between these three quantities? Sine. This is sine. The sine of the angle theta is the opposite, which is 10, over the hypotenuse, which is x. That's the relationship that exists between theta, 10, and x. Everybody good with that? Don't want tangent, don't want cosine, because that would be using the adjacent side, which is where the water is, and I don't know that value. All right. This right here, then, is what we're going to differentiate. So let's do that next. What's the derivative of sine of theta? It is cosine of theta, and then we're going to write d theta dt. This is all differentiation with respect to time. That's a good thing. D theta dt is what I'm looking for. Now I've got at least part of an equation where d theta dt is actually involved. What about the other side? Well, I could have written this just as awareness here as 10x to the negative 1. So what is the derivative of 10x to the negative 1? Good. And then dx dt. Because you see, I still need, this is, what we're doing is we're doing chain rules. That's what implicit differentiation was when we talked about it before. Implicit differentiation is chain rules. So when we're taking the derivative of this piece right here, I take the negative down, and then I change the power to the negative 2. But then I need to take the derivative of x itself. Well, normally I'm taking the derivative of x with respect to x, so that's just 1. But I'm not here. I'm taking the derivative of x with respect to time. So that's x prime, or dx dt. And I like writing it, especially in this section, as the dx dt because it helps remind us that these are ratios, right? This is something with respect to time. I'm going to get units that are going to have a value with respect to something else. It's a rate. Some of these things I know. I know x. It's 25 at the given point in time I care about. I know dx dt. It's negative 1 at the time I care about because it's negative 1 always. I'm looking for d theta dt. which means I need to be able to find the theta in order to make this work. Does that make sense? I have to substitute in everything except for the quantity I'm looking for, the d theta dt, which means I have to figure out what theta is. And I can do that. How in the world could I figure out what theta is using this sketch? Inverse is the one you want. Inverse sign. Yeah. So if you take a look over here at this quantity, we know, and we wrote it down a minute ago, that sine of theta is 10 over x, right? And at a given point in time, we know that x is 25. Well, that's the point when we want to know what theta is. We want to know what theta is when x is 25. So I can set this up so that the sine of theta is 10 over 25. Then we can do exactly what Nathan said. We can do the inverse sine. So we can find out that theta is sine inverse of 10 over 25. And your calculator will do that just fine. A reminder about your calculator as you're doing this. I don't think I'll have a problem with it, but this is in radians. Okay? And the reason we have to use radians is because all of the derivatives that you know and love now about sine and cosine are all based in radian measures, not degree measures. So we need to make sure that we're working still in radians, and your calculator should already be set up to do that. So someone find for me the value of theta, and let's go with 6 decimal places, just to keep things sort of long and unrounded, so that we don't have any rounding errors. So what is theta?
0.411517.
Okay, 0.411517. Are we all good with that? Okay, so now I have an angle measure, I have a theta. So over here in my problem, I know theta, I know x, and I know dx dt, which means I can find d theta dt. So we're going to insert those quantities in. We're going to do the cosine of 0.411517 times d theta dt equals negative 10 over, and I'm going to put it as a denominator because it had a negative exponent, so 25 squared times negative 1. All right, so we've got our d theta dt. This would have actually been the same as having 10 over 25 squared, and then all of that divided by the cosine of 0.411517. What did we find for d theta dt? We'll go with 4 decimal places because I think this is a pretty small number it gives you, right? Did you get one, Tyler? Almost. Do you have one, Hannah?
0.0175.
After 0 out. Look good? Okay. I need units on this. And this is, again, where it's really nice that we've written it sort of in this way instead of just writing theta prime. What are the units on theta?
Radians per second.
It is radians, and the time is in seconds because the original problem was given time in seconds. So you can sort of mirror it back to sort of the ratio as it's described on the left-hand side to remind you how to do the units. This is in radians per second. Okay, make sense? Everything with related rates is going to be relating to quantities that are changing. Ready to try another one? All right. The next problem algebraically is easier, but it probably involves something that, well, it involves something that some of you might not remember how to calculate. So the spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. And then it says how fast is the radius of the balloon increasing when the radius is 30 centimeters. What do I do first? Draw a picture. And my picture will look like a what? A circle. and then we're going to sort of turn it three-dimensionally into a sphere, right? So my picture looks something like this. And there's my radius in the middle. Now, the size of the balloon's changing, right? I mean, we're airing the balloon up. So the radius is actually changing, which means it is a variable r. It is going to be a quantity that's changing. But at some point here, I'm going to actually use a value for r that's equal to what? 30. So let's put in the information that we know. We know that at some point, we're going to plug in r equal to 30. It's 30 centimeters. I'll write centimeters for now. What else do we know? Yeah, something about this. This is a rate. There's a rate of 800 cubic centimeters per minute. But what is that? I mean, it's a rate, so it's something over time, dt. What over dt? Well, we could call it dx, but what would x be represented in terms of the issues of this picture, the context? It's volume, so let's use v instead. This would be dv dt. So when we're talking about a three-dimensional object and the space inside of it, that's a volume quantity. So it's actually the volume of this object that's increasing, right? The whole amount of space it actually takes up. So this quantity that we actually know is dv dt. What are we looking for? What is it we want to find? How fast the radius is doing something. So what quantity is that in terms of these notations? It's a rate, right? So something over dt. It would be dr dt because it's the radius that we're changing. So this is what we're trying to find. We're trying to find dr dt. So the whole issue here is about the volume of this balloon, that is the volume of a sphere. Do you remember the volume of a sphere formula? It's 4/3. What's next? Pi r cubed. Volume is in cubic measurements, so you're going to have three variables, so r is cubed. So a couple things here. I bring this in as the second problem. What we're doing after this is really easy. This problem is actually much easier to work out than the last problem. The thing I want you to be aware of in this particular problem is that if you encounter a quantity that you don't know, you guys have phones with you. You're not going to have phones on the test, I know. But you have access to internet. You have your textbook, which probably has these formulas in the front or the back flap. They usually do. Don't be afraid to grab something out and to try and figure out what that formula was supposed to have been, okay? When I create something on the test, it will be a formula that I know you know, all right? I would not assume that you knew the formula for the volume of a sphere. That's kind of a specialized piece of information. So I would expect that you might have to look that up if you couldn't remember the details, okay? All right, so we are going to do what now with this quantity now that we do know this equation? We're going to take the derivative. So what's the derivative of the left-hand side? dv dt. What is the derivative of 4/3 pi r cubed? Okay, let me write the 4/3 and the pi down. Those are just numbers, right? And then what's the derivative of the r cubed, Micaiah? 3r squared. And then what do I need? dr dt, yeah. Remember, this r is a variable that's changing with respect to time. So when I take the derivative of the r cubed, I have to take the derivative of the r itself, and the derivative of r itself is dr dt. It's sort of a hidden, if you will, inside derivative, like a chain rule. The nice thing about this is that this 3 and this 3 simplify, right? So this dv dt could actually be written as 4 pi r squared dr dt. You know what, let me leave it there for now. We know most of these things, don't we? We know dv dt. We know r. 4 and pi are just numbers, which means we should be able to substitute in the dv dt and the r and solve for dr dt. So we have 800 on the left equals 4 pi. R is 30. So it's 30 squared then on the right, dr dt. All right, so we have 800 equals 4 pi times 900 dr dt. So dr dt would be 800 divided by, what's 4 times 900? 3,600 pi. If you want to simplify a little bit, you could probably mark out the hundreds. So in terms of putting it in your calculator, dr dt is 8 over 36 pi. I know you could simplify the 8 and the 36 too, but at least at this point it's easy to put in your calculator, so you don't need to simplify the piece right here. What is 8 divided by the quantity 36 pi? We'll go with 4 decimals again. It's got a decimal.
0.0707.
Mm-hmm. You want to take a stab at the units? You think they might be? Mm-hmm. So it's centimeters. Remember, you can go back to what it looks like on the left-hand side. R is on top. R is measured in centimeters. T is on bottom. Look back in the problem. How are they measuring time in this particular problem? And it's minutes in this particular problem. So this is centimeters per minute. .0707 centimeters is really small. That's smaller than a millimeter. And if you think about your rulers, your millimeter is the tiniest little increments that they ever mark on the rulers for you. So this is increasing pretty slowly, isn't it? It's pretty slow. Per minute? Crazy. Yeah. Okay, any questions on that one? Okay, the last one. The last one has a couple of interesting things involved, and is definitely the most complicated one, which is why I'm putting it last. Oil spills out of a tanker at a rate of 900 gallons per minute. The oil spreads out in a circle. The circle has a thickness of 1/8 inch. Determine the rate at which the radius of the spill is increasing when the radius reaches 100 feet. Okay, first question, can you picture in your mind what's happening? Can you visualize what's going on here? Whether you can draw it or not is not the issue right now, but can you envision what's happening? Something is dumping oil out on the ground, and the oil is spreading out in a circular pattern, which is how most liquids will spread out if you dump them out. Water will do the same thing, okay? Oil is a really nice example here because it has a thickness that they're talking about. It doesn't just sort of dissolve into the ground, so it has this sort of a uniform way in which it's spreading. It has a thickness. It's like if you were doing something with glue. Glue would do this too, right? Where it spreads out, but it doesn't spread out indefinitely. I mean, there's still a thickness to it. All right, so we've got oil spreading out in a circle, okay? So the image that we actually are going to draw is a circle. Now, the circle actually has a thickness to it, which means we don't really have a circle. What do we have? What's that shape? It's a what? What did you say? An oval. Okay, it looks kind of like an oval. It just looks like an oval because I'm drawing it from the side because I want to draw a dimension. It's a cylinder. Okay? So imagine a, well, you know what? This over here works pretty well. The base of this, if it were flat instead of height here, this is the image that we have. We've got a circle with some thickness to it. That's a cylinder. It's a really thin cylinder. I mean, 1/8 of an inch is not very thick, okay? But, and the other thing that's important to realize is that the 1/8 of an inch, that 1/8 isn't changing. Because they tell you that the height of the circle, or the thickness of the circle, is actually 1/8. It's a fixed thickness. So this 1/8 is actually fixed. But yeah, we've got a cylinder here. Let's write down some things that we know. We only know it's a cylinder, but beside that, rates and quantities that we know. What do we know? Oh, I should have marked my radius in here. Let me do that. First of all, the radius is changing, right? Because the oil continues to be spilled out. What quantities do we know? There's some rate of 90 gallons going on here, right? What is this a rate of? It is volume. It's the amount of it, right? The size that this is spreading out to, it's the amount, that's volume. This is dV/dt. So we know that dV/dt is 90 gallons per minute. What else do we know? One more piece of information that we know. The thickness, but I've already got the thickness labeled. Something else that I haven't labeled yet. Yeah, this last piece of information about that at some moment in time the radius has a quantity. So the radius at some moment in time is going to be 100 feet. Does that make sense to everybody? What are we looking for? What are we supposed to find? dr/dt. The rate of how the radius is changing. So we're looking for dr/dt. So we need a formula that relates volume and radius together for the shape of a cylinder. So I need a volume formula. And again, you may not remember this one, but does anybody remember what it might be? I bet you can come up with it. What's the area of a circle? Pi r squared times the height. All a cylinder is the area of the top piece, the circle, times how tall it is. Yeah, so it's actually pi r squared times height. All right, now there's a problem in this problem. There's a confusion, there's a problem with the values that we're given and using them. Does anybody see what there's going to be an issue with here?
The heights in inches, and radiuses in feet.
That's part of it. The heights in inches, the radiuses in feet. And the volumes in gallons. That's a problem. Notice on the other problems, the other examples that I did, none of that happened, right? This is in feet per second, and I'm given feet. This one was in centimeters and centimeters per minute. And I've got 3 different quantities here that are not reconcilable at the moment. They don't match. So we're definitely going to need to make them match in order to use them in the same formula. I mean, it won't work if I just use the numbers as is. They have to match. The units have to match. So the feet to inches isn't a problem, right? I mean, you guys know how many feet are in inches. Or how many inches are in a foot. The problem really more is with the gallons issue. That's weird. I mean, like, how does gallons fix with feet and inches? I mean, like, that's odd. So let's actually take a moment and take a look at reconciling some of these issues. So one of our issues is the feet. We have 100 feet at some point. And what we're going to do is we're going to figure out how many feet are in an inch. So you tell me, how many feet in inches? How are they related? 12 inches equals 1 foot. And you should have seen this kind of a calculation in your chemistry classes before. 100 feet is going to be feet on bottom, so the feet will cancel. 1 foot equals 12 inches. These quantities are equal to one another. Trying to blanket what they usually call that when you do the analysis. What do you guys remember what this is called? Say it again. What is it? Yes. The what analysis? Dimensional analysis. Thank you. Yes, dimensional analysis. And we can decide just by what's going to cancel out where things go. The feet are going to cancel here. So I have 12 times the 100. So how many inches is this? Thank you. You guys are shy today. 1,200 inches. Yes, 1,200 inches. So if I come back over here in terms of this problem, this is equivalent to 1,200 inches. Let's look at the 90 gallons one then, because that's probably not one you know. I want gallons to be turned into something that's inches. I mean, that's got inches in the rest of the problem, so I need it into something in terms of inches. And the actual ratio is that 1 gallon is equal to 231 inches cubed. And not going to lie, I looked that one up on Google. There's no way I would have remembered that. I don't know that I've ever even seen that used before. I wanted to use it though because there's a couple in your book that are going to take this gallons idea and convert. And I wanted you to recognize that just because they give you a quantity doesn't mean that you have to actually know the relationship in order to find the relationship. Okay, you guys have lots of resources to be able to find this information. So if there's some kind of a conversion that you need to make, simply look up what the conversion should be and make it. Okay, if you were working with centimeters and inches, you might not know that particular one either. You might, but you might not. So don't be afraid to look up the conversions that you need to make. So on this one, the gallons are going to go on bottom right, and then the 231 cubic inches will go on top. So my gallons will cancel, and you're going to find out for me what is 90 times 231.
20,709.
All right, so these are the two quantities that we needed in order to be able to use this problem. 20,790 inches cubed, and then 1,200 inches. And this is inches cubed per minute. I should have written it per minute over here. And the minutes will still be part of the answer, or part of the quantity. Okay, all of the units now match. They're all in inches, and that's what they need to be. They all need to match in order to use them in the problem. Now, this problem over here, I wrote down volume equals pi r squared h. But h is not a variable in our problem, is it? What value is it? 1/8. It's always 1/8. It's a constant 1/8. It's not changing. Okay, the oil pours out and it automatically spreads to a level that's 1/8 of an inch. So that quantity, before we do any derivatives, needs to be put in there because it doesn't change. We don't put the R in or the V in or anything else in because those quantities are changing. And we need those to be actually represented as variables because they're changing. But the height isn't changing, so it doesn't need to be written as a variable. Now we can actually take this derivative, though. So what is the derivative of V equals pi r squared 1 times 1/8? In fact, I'll write the 1/8 at the beginning just for clarity. What's going to go on the left? dv dt, you bet. What's going to go on the right? The 1/8, oops, hang on. The 1/8 and the pi are going to go there, and then what? 2r dr dt. Okay, so is everybody good with that? Okay, only do one more cleanup step. dv dt equals pi r, you know what, we'll do it this way, about 1/4 pi r dr dt. All right, everybody good so far? What was dv dt? 20,790. 1/4 in pi, r 1/4 in pi. What's r? 1,200. And dRdt is exactly what I was looking for. You can do one step to clean up if you'd like right here just to make it easier on you when you're entering in the calculator. That 1/4 and that 1,200 is 300. So this is 300 pi. So dRdt can be represented as the 20,790 divided by 300 pi. That is 300 times pi. I think 2 decimal places is probably sufficient on this particular problem. I used 4 on the last two just because the numbers were quite small. They were decimal answers. This one's not, I don't think. So what do you get for this particular answer? Make sure you're putting parentheses around the 300 and the pi so that those are multiplied before they use the division. Did you get a quantity, Austin?
22.06.
I think that sounds right. Jamie, is that what you're getting? Brooks? Brooks is nodding. Okay, good, good. We've got 3 people who got that value. Good. What about units? Inches. Is it inches cubed or inches? Inches, per minute. Now think about what that just says. Inches per minute. 22, that's almost 2 feet. The radius of the spill is increasing almost 2 feet per every minute. That's really fast, isn't it? But if it's dumping out 90 gallons per minute, that sort of makes sense. Yeah, I mean, this does seem like it should be increasing quickly. Agreed? Yeah, because you should have some sort of in your mind what 90 gallons looks like, right? 90 gallons of milk, something like this, right? It's a lot of milk. It's a lot of oil. Any questions on that? You have a very similar one to this that you're going to work on in your homework. All right.